While working with Lean, it's actually impossible not to notice the humongous role played by inductive types. They are displayed first and foremost together with their constructors. However, to actually use an inductive type, it's not enough to have just the constructors, right? You need a way to actually break apart the constructed values before you can use them. And that's precisely where the recursors come in. So my aim for this video is that by the end of it, you have a better understanding of what recursors are, why they matter, and how they are used to power a lot of things we do in Lean. The plan for this is as follows. First, I'll quickly go through the three kinds of rules that come with every inductive type. They are the formation rules, the introduction rules, and the elimination rules. Then we'll kind of focus just on the elimination rules, and I'll walk us through many examples, starting small and building up to the natural numbers. Finally, we'll see how the recursor combined with the constructors in order to get us the indispensable computation rule. So let's get started. Okay, so the concept here is that every type has some kind of API or application programming interface that makes the type usable. This interface consists in what we call rules. So the first rule is the formation rule. It's probably the simplest one to understand. So let's say we define the type of pairs as such. Okay, so we have the type of pairs here, and if we want to talk about this type we've just defined, let's say we want to talk about it when writing some function signature or something like that, we want to write this, right? So to be able to talk about it, that is to be able to form the type, we see that we need two other types, alpha and beta. This is basically the formation rule. To form this type, you need such and such. Hence, the formation rule in general is just given in Lean via the type constructor, which is here. Once again, in the pair case, it would be given alpha and given beta, which are two types. You may form the type pair alpha beta. In case we have, let's build another type, let's make the unit type. Okay, so here I'm getting an error because unit is already declared in the by default namespace. So let's just create a new one called hidden just for the purposes of this video. So here we have a type unit, which is probably one of the simplest type you could ever build. There is only one constructor, which takes no arguments and just produces a value of type unit. And we see that the formation rule here simply says that we may, in any circumstances, form the unit type. And that's simply because there are no parameters to this type constructor here. If you contrast this with the pair situation where we have two types needed to construct the type. Okay, so the formation rule just tells you when something is a valid type. Introduction rules tell you how you can construct a term of the type you've just defined. In Lean, this is governed by the list of constructors to your type, right? Each constructor corresponds to an intro rule, and every intro rule is basically just a constructor. For instance, in our pair type here, you have a single constructor called mk, which says, given a value x of type alpha and a value y of type beta, you may construct a term of type pair alpha beta namely the term mkxy. Right, and this is given that x is of type alpha and y is of type beta. Let's define another one. Another type. Let's define the sum type. So we have here the sum type, which is interesting in this case because it has two constructors, as you can see. So there are exactly two intro rules for this type. For instance, injection left is the intro rule, which says, given a value x of type alpha, then you may form the term inil x of type sum alpha beta. So let me write this more clearly. So given some x of type alpha, you may construct the term in left x, which has type pair alpha beta. Oops. Sorry, I'm having trouble. Okay. So this type here, it has two intro rules. Similarly, we can construct the natural number type as follows. And this type here also has two intro rules, right? The first one says that you may always form the term 0 of type nat. And the second one says that given a value little n of type natural number, you may form the term successor of little n, which also has type natural number. Notice that this intro rule here, it is cool because it is truly recursive in the sense that it refers to the type it's attached to. So, for instance, by two intro rules, we can check that this term here, say check this term right here. So this basically the term that's supposed to mean 1, this has type natural number because of two applications of intro rules, right? This 0 here will type check as a natural number by the first application of this intro rule, and then when we apply the successor, this is another application of the second intro rule, which says that this has type natural number. As you can see, there is a problem here because it doesn't know what I mean by this identifier. The problem here is because I need to put myself in a namespace where these symbols may be recognized. So let's put ourselves in this namespace. And yeah, we see it succeeds now. There's also a special type, which I guess I could describe here, which is the empty type, which is defined as follows. And we put nothing under the where because there are no constructors for the empty type. It's impossible to construct a term of it. So each constructor is exactly one introduction rule, and every introduction rule is just another way of saying constructor. And the constructors, they are the only effective way of building values of a given type. The elimination rule is where the magic starts to happen. This is called the recursor by Lean. So, okay, the last two rules were quite nice and easy to understand since they are apparent when we write the definition of our types. The formation rule is given by the parameters to the type, and the intro rules are given by the list of constructors. On the other hand, the elimination rule is not apparent, since it is mechanically generated for us by good old Lean. Yeah, and like I mentioned, Lean calls it the recursor. We can look at what it looks like with the command check. For instance, here's what the recursor looks like for the natural number type we've defined. You see here. So we'll go through this. Don't worry about it. Here's the recursor for the sum type. Once again, don't worry about it. We'll go through everything and you'll understand perfectly what's going on here. So the recursor is basically a rule for consuming a value of a type. For instance, let's start simple with the recursor for the unit type. I'm going to explicitly write out the type of the recursor so that it's easier to read. And in order to get rid of this error here, I'm just going to put ourselves into the unit namespace. Let's close all of this just so that there's not like too many things going on the screen. So, okay, this type checks. So we know this is actually the correct type for the recursor here. And what this says is that to construct this function here, so to construct a function from the unit type into motif u, it suffices to simply give an element of type motif star. This is what this is saying, right? Like this function here, if you give it this argument, it will construct for you a function from the unit type into motif u. The purpose of the motif is to specify the type we want to construct given an element of type in the type unit, right? This may seem a bit strange since it kind of stands to reason that the only element living in the type unit ought to be simply the term star itself. After all, to make a term of type unit, there's no other way than using star, as you can see here. We know that a function from a domain having only one element is the same as just choosing an element of the domain, right? Like if you have a function and there's only one thing you can feed to the function, then it will point, the function itself will be like a pointer onto something in the codomain of the function. So a function from a domain having only one element, like unit would have, is the same thing as just choosing a type, right? Okay, so couldn't we just change motif here so that instead of being a function from some choice having supposedly one element into type, it would be just simply a type, right? Why does it have to be a function here? I mean, this is a great question, and this is a really important, it seems like just a technical detail or something, but it's actually really an important consideration and kind of a deep question. Having a single constructor like we have here, that is actually, it's not enough to prove that there are no other elements in unit, or it's not enough to prove that there are no other terms of type unit. If you haven't noticed, at no point did we ever say that the only permitted terms of a type were those made using constructors. What we said was that constructors are the only possible way to construct a value of a term. So maybe some terms come into existence at the same time as the type, and so they would exist without us needing to actually explicitly construct them. Would be weird, but could it be possible that such far out, inaccessible terms live, a bit like parasites, somewhere inside of the unit type? Well, no, of course, but to prove that there aren't any other values like other than star in unit, you need to actually use the recursor in your proof. Since the motif must be specified as an argument to the recursor, it can't use the knowledge that unit contains only star, because at this point, we don't know that yet. The fix is to specify the motif, the fix is to do that, specify the motif as a function from unit to type, so that we can apply any term of type unit to that function without needing to have prior knowledge about how the term is made. So the motif is the type we want to construct given any element in the type unit. Now each constructor in the type corresponds to a parameter of the recursor. Continuing with the unit type, we see that the unit constructor here is star. It corresponds to the first non-motif argument, right? And if we consider that the return type of the recursor is actually a function, then that argument right here is actually the only explicit argument to the recursor. That means that to define a function out of the unit type sending u into motif u, it suffices to specify what the function should be in the special case where we actually have the knowledge that u is the constructor star. So even if there actually exists some far out element in the unit type, the recursor says that these far out elements, they are actually irrelevant. In other words, we can just ignore them. In this sense, these far out elements, let's say they are inaccessible and they are impotent. So they may as well just not exist, right? So we can even, like I said, using the recursor, we can prove that there are no such far out elements. We can settle this once and for all. We will call this theorem unique. And it will say that it will confirm our belief that the actual only element in the unit type is star, as we would expect. But as I said, we need to use the recursor. So for any term of type unit, we want to prove that u is basically just star. And we can prove that using the recursor. Let's use when I put this at symbol here, it means that I want to explicitly specify every argument, even those which would be implicit usually. The only implicit argument here is the motif, so what I'm saying is I want to specify explicitly what the motif should be. We'll do it as a lambda abstraction. Okay. Or you know what? No, I want to show you that Lean is able to figure out what the implicit argument should be by itself. And as you can see here, what we need to put inside this hole is a term of type star equals star. This is easily proven using reflexivity. Sorry. And there you have it. This is an actual proof that the only living inhabitant of the unit type is the star term. So just to resume, right? The recursor makes it possible to define function out of your type by saying what the function should be when applied to constructors. In the unit case here, we have very simple types, so maybe it's too simple. So let's go see more example of that, and things should become clear. The next example we have here is the pair type. So what does the recursor looks like for this? Let me write it with its type really prominently displayed. as you can see, we have the same concept here of the motif, but this is not all. I said we need to have one explicit parameter for each constructor. The pair type has only one constructor, so there's going to be only one explicit parameter. But since the constructor mk takes two arguments, this first parameter here is going to also take two arguments, right? And if it's not already clear, you'll see why in a moment. And again, I forgot, let's put ourselves in the correct namespace. So, like the unit type, the recursor here, if we see its output type to be a function, then the recursor, it has only one parameter, one explicit parameter, I should say, which is this one. This parameter, like I said, it corresponds to the unique constructor mk of the pair type. Since this constructor takes parameters, these parameters are reflected here, x and y. Morally, we should always be able to break down the pair into its two components, x and y, right? X and y. However, this thinking already implies the knowledge that any element of a pair type is obtained from an application of the mk constructor, like this pairing constructor here. But, I mean, what about those far out elements I was talking about that may or may not exist? Again, the recursor says that those possible strange elements, they don't matter, so they may as well not exist. It says, the recursor says that to define a function out of the pair type here, sending some pair p into motif p, it suffices to specify what the function should be in the special case where we actually have the knowledge that p is constructed using mkxy, right? This special case right here. The two parameters x and y that you see here, they are the two components of that pair. So in this special case, when you're trying to construct this argument that you must pass to the recursor, you actually have access to the components of the pair via these arguments here. So just like with the unit type, we can also prove that, just like we believed, every pair is made up of two components, right? If you come at this from like a set theory perspective, this seems to be a non-theorem, since pairs are defined in set theory as basically everything that can be paired up. So it's really obvious that every pair can be broken up into two pieces. However, here we're not defining pairs like that, so try to keep an open mind and think about these possible out there elements. So, you know, we can actually prove that every pair can be broken up into two components, but again, this knowledge, it wasn't available to us before. So you can, if you want, it's a nice exercise to try to prove a similar theorem as this unique one we did for the unit type, but for the pair types, that says that every pair can be broken up. So I guess this is left as an exercise for the viewer, but you may want to wait a bit before you try it. I mean, until we've covered the computation rules. Okay, so for a final example, let's investigate the recursor for the natural numbers. I will explicitly write the type again, just so it's easier to read. There's the motif again. All right, and here I'm having some problems since I wrote the, the wrong thing here. Should be like that. And also, we should put ourselves in the correct... I did the wrong thing, but it's okay. I'll just take this and replace this here. And what is missing, we need to put ourselves actually in the namespace n. Let me just do this like that. And I'm wondering why it's screaming at me. Oh, because I'm missing a parenthesis. Okay. Everything type checks. So this means this is the actual correct type for the recursor that Lean generated for us when we define the natural number. The motif is the same thing as before. In the two previous examples, it had exactly this form, right? So this is the type we have defined, and the motif will take some term of this type and produce a new type. Sorry about that. The big difference here is that the recursor has two parameters, since our type has two constructors. And I should say it has two non-implicit or two explicit parameters if we consider the recursor to produce a function here, which is what we want to do. So natural numbers have two constructors, hence our recursor has two explicit parameters. The first parameter here corresponds to what our function should produce when applied to the zero constructor, and the second argument here is the most interesting one. That's because the constructor here is it's truly recursive, as I said earlier. You know, its parameters is a natural number, and that's an element of the type it's a part of. But okay, as before, we intuitively think that any term of type nat is either 0 or some chain of plus ones, like some chain of applications of this constructor here. So this recursor is the thing that formally justifies this belief. It says that to define a function on the natural numbers sending n into motif n, to define this, it suffices to say what happens in two special cases. What happens when the number is 0, just like I said earlier, and what happens in this special case when we have the knowledge that our number is constructed using successor and that we have in the past already constructed a value of type motif n, right? Notice that this gives us the possibility of using the value of type motif n in our construction of this term here. It's like saying, you know, here's how to handle 0, here's how to handle the successor, now handle any natural number. And said in yet another way, the first argument here is the base case, while the second argument here is the inductive step. Now, I do hope this explains the name recursor, right? And this name is because when we look at what happens, like how Lean generates the recursor for our type nat, we see it's exactly the principle of definition by recursion in mathematics, or as I should say maybe in classical mathematics, I don't know. But in fact, if we allow here propositions as well as type, which is possible, we also get the principle of proof by induction, not just definition by recursion, but also proof by induction. For instance, we can let's slightly adjust this so that we may construct any sort instead of just types. I will need some universe level here so that it doesn't scream at me, but now we allow the recursor, or rather I should say we allow the motif to produce something that is not only a type, but it could also be a proposition, right? Remember that propositions are just sorts at level 0, while type is like sort 1 and so on. Therefore, when u is equal to 0, this becomes just prop, right? This is a special case. This is sort 0 or prop. And that means that the motif here, it starts to produce propositions. So for every natural number, you get a proposition. We have a term for that. We say that motif is a predicate on the natural numbers. And now the recursor says that to show the predicate motif is true for every natural number, which is exactly this. So to show this is true, it suffices to show the predicate is true at 0, and to show that the fact it is true for n implies it is true for n plus 1. I mean, this is exactly proof by induction, right? So the recursor kind of subsumes both proof by induction and definition by recursion. So it does a lot of things, right? It makes it possible to define functions out of your type. It makes it possible to do that by saying what the function should be on each and every constructor of your inductive type. So in this very specific sense, or maybe I should say in this very vague sense, like the opposite of what I just said, but you know, the recursor is kind of like the dual of constructors. I mean, just like constructors are the only effective way to build elements out of your, they are the only effective way to build element of your type. The recursor is the only effective way to build function out of your type. And I mean, building functions out of a type is precisely what using value of a type means. Right, so to conclude this part of the video, you can try this exercise if you want. Look at the type of the recursor from the sum type here. So look at what it does when you do check of at sum rec. Like look at the type of the recursor for the sum type. And then try to describe how it corresponds to the technique of proof by case analysis. And if you want more, you can do the same for the recursor of the empty type here. And you can try to describe how it corresponds to the principle of explosion. The principle of explosion is that from a contradiction, one may prove anything. If the recursor makes it possible to define functions out of your type by saying what the function should produce when applied to constructors, then it stands to reason it should be possible to compute a function defined using recursion when it is applied to a given constructor. And this is precisely the job of the computation rule. So the computation rule, in other words, is what makes it possible to reason about constructions we made using the recursor. Said fancifully, it gives computational meaning to our constructions. So let's go back to the unit type right here. Recall here the recursor makes it possible to define a function from the unit type into motif by specifying how this function should act on the unit constructor star. Then it stands to reason that when one applies that new function right here to the element star, it should produce like what is expected. Okay, I will express what I just said more clearly by writing a theorem that I will go compute. So what I was saying is that given any motif and given any chosen point, like any choice of point in motif star, we obtain this function right here. Right? This is the recursor that we have applied to its two first arguments, and what we get back is this function here. So this is a function. If I apply this function to star itself, right, I get back the chosen point. And this is going to be true by reflexivity. Okay, let me explain a little bit what's going on here. This function, what is its type? Well, it's a function that takes any element of unit and produces something of type motif U. Well, star is definitely an element of unit. It's the canonical element. So we can apply this function to star. And what this is saying is that, okay, well, this function right here, it is defined by saying what should happen when I apply it to star. And what should happen is it should produce the value point. So yeah, this is what we get here. And the really important point is not that this is true. The important point is that this rule is true judgmentally. So superficially, the terms here, unit, this function application here, this term, and this term on the right-hand side, they may look like quite different, even though we know we just proved they are equal. But you know, if we just look at how they're written syntactically, they seem really similar, different. Lean, however, is actually unable to tell the difference between them. That's because when we define the type unit, Lean added to its internal state that the term here, it will compute or reduce to the term here. So since Lean can only tell the difference, it can only like tell terms apart up to being reduced, let's say. These two things, in the eyes of Lean, they are literally the same thing. That's why we can use the reflexivity here to prove that this is true. Hey, so it's future me. And yeah, I'm currently editing this video, and I realized I should have explained the concept of judgmental equality in maybe a different way that's simpler. So a judgmental equality is when you don't need to prove that two things are equal, right? You don't need to give Lean a proof that two things are the same, because Lean just sees no difference between them. So if you replace some, you know, if you replace the left-hand side with the right-hand side, in the eyes of Lean, it's just like you did nothing. For instance, there's the command reduce that can reduce stuff for you. And if we try to reduce this, just say star here, then what's going on? Oh yeah, I wanted to put this, and this is going to be a natural number. So I'm using the built-in natural number type in Lean instead of the one we defined, just because it's easier to, but we could build a function using our own type. It's just easier to do it with the built-in nat. So here we see we get 0. So this expression here, it reduces to 0. Therefore, in the eyes of Lean, there's no difference between what I've highlighted here and just simply 0. And the reason this works is because of the computation rule. So let's go and see what's like how this works for this type, our type of natural numbers, because we have two constructors. So things are a bit different. Since we have two constructors, we must have two computation rules. We have first one, which describes what happens when we compute on the first constructor, what happens when we compute on 0. And like I said, there are two constructors, so even for the recursor, we need to specify two things. There's the base case and there's the inductive step case. So our theorem right here, it will render explicitly what happens when we apply this function here. In parentheses, this is a function that's defined using the recursor. When I apply it to the 0 constructor, I get back the base. What I specified should happen at the base, and in the 0 case. And this is going to be true also by reflexivity. And so this says we have this function here that's defined using the recursor. We defined it by saying it should produce base when applied to 0. So here we have the confirmation that this is what it does. There's a similar theorem, albeit it's a more complicated one, about what happens when we compute on the successor constructor. And yeah, this needs to take as another argument some integer. And then what do you think will happen here? Well, it's going to produce, we said in the inductive case, we need to step something. And here it's going to be this function here. Oops. And this is also going to be true by reflexivity. But okay, I understand this may be like more complex to understand. So let's just use a let statement to our advantage. I'm just going to rename this long thing here to be f. This means here, this is just f applied to n. And I hope now this is clear, right? This says that f applied to n plus 1, or f of n plus 1, is the step function applied to the previously computed value. So imagine this is the result of doing a recursive call. And then this is, okay, what should we do with that result? And yeah, this equation right here, this is really the essence of definition by recursion in classical mathematics. This is a direct consequence of the computation rule in Lean. For instance, we can use that to, like, I want to illustrate something. Let's say we have a multiplication operation on the natural number. We could define it, but I'm just going to assume it as an axiom, just so we don't get too bogged down in the details, right? So let's just assume we have something that's called multiplication, and it does multiplication like you would expect. Now I will define a factorial function because, yeah, I know this is not the most original thing ever, but bear with me. We will define that using the recursor. Okay, so the first thing is the base case. So what is 0 factorial? That's just 1. You can write it like that. And here we need the induction step, or like how to compute the factorial for n plus 1 given the factorial for n. So let's write it like that. Do a lambda abstraction. So we have n. We have the result of doing n factorial. And you want to compute what is n plus 1 factorial. Well, you know, that's just going to be n plus 1 times p. And this gives us the factorial function. We can check that this works by using the reduce command, and then just writing the factorial of let's do 2. Let's do the factorial of 2. So like that. And here, okay, this is terrible because there's a lot of field notation everywhere, so we can use this handy little set option. I think it's that. Yeah. Okay, yeah, that's better. So we can see that this call here, it reduced to this, which is the correct thing. If you can see, we have here this inner multiplication is just 1 times 1, and then here this outer multiplication is it's 2 times 1. So this is 2, and you see the pattern here, right? If we would have used the factorial of 3 instead, then we get this, which is 3 times 2 times 1 times 1, and that's the correct thing. So the fact that this is the expected answer is actually a direct consequence of the computation rules. So to resume, the computation rule enables Lean to reduce terms defined using the recursor. So every time Lean computes something, it actually applies these computation rules. Lean cannot really make the distinction between two terms that compute down to the same thing, so this makes it possible to reason about definitions we made using the recursor. And that's really the whole utility of this rule. I hope this video helped you understand the theory behind the recursors and gave you deeper insight into Lean. We saw that every inductive type comes with three fundamental rules. So formation rules tells us when we have a valid type, introduction rules show us how to construct values of that type, elimination rules, which is the mighty recursor, they give us the only meaningful way to use those values, and to use those values we really need the computation rules. So all of these rules are necessary to make inductive types work in Lean and in type theory in general. To me, the recursor seems to be the mathematical essence of what it means to use an inductive type. It's basically the formal justification for why we can reason about all possible values of a type by just considering its constructors, which is pattern matching, right? It's what happens behind the scenes when Lean compiles a match statement. It compiles it into usage of the recursor. So each branch of the match will correspond to one of the explicit parameters we saw given to the recursor. So the recursor and the computation rules are basically the bridge between the world of constructing values and the world of reasoning about them. So if you master them, you basically master a fundamental principle of type theory that underlies all of functional programming. So thank you for watching and happy proving!